So today we're going to be talking about instantaneous rate of change. In our last video we talked about how to find the average rate of change. Today we're going to try and narrow that down and be more specific and say how can I determine how quickly something is moving or what the instantaneous rate of change is at a particular instance. Now the problem that we run into with this is that when we're doing the average rate of change, we're looking at the slope of the secant line, and you can see that I've put the pretty much the same image that I had up here before when we were talking about average rate of change. I've got my function f of x, and I've chosen 2 points, x and x plus h. This is the ordered pair x f of x. This is the ordered pair x plus h f of x plus h. And when we were doing average rate of change, we found the slope of the line that connected those 2 points, and so I took the difference in the y values, f of x plus h minus f of x, and divided by the difference in the x values, x plus h minus x. But that just gave me an average of what was happening over some period of time. And I can, if I want to, get a better and better average of what's happening at exactly x if I move this point x plus h closer to x. So right now, just kind of sketching in some things, I would find that the slope of the secant line would be the slope of this line here. But if I move x plus h even closer, and I say, okay, let's let x plus h be over here, now there's my x plus h, and now I get a better approximation of what's actually happening exactly at the value or at the ordered pair x f of x. So the closer that I get these 2 points together, the better my approximation is. The better understanding of what I have, of what's happening at exactly x f of x. But I can't get those 2 points to be exactly the same. If I get those 2 points to be exactly the same, then I'll only have 1 point to work with. And if I only have 1 point to work with, then I can't use my slope formula. I can't use the difference in the y values divided by the difference in the x values because I have the same x values and I have the same y values. So to resolve this issue, we're going to use limits. And what we're going to do is, okay, I can't say that the difference between x and x plus h is 0, because if they say the difference between x and x plus h is 0, then I just have 1 point. So what I'm going to do is I'm going to say, well, I want h to get really, really close to 0. And the way that I'm going to do that is still going to take the difference in the y values divided by the difference in the x values. But what I'm going to do is I'm going to say, what happens if I take the limit as h tends to 0? As h gets really, really close to 0, what's happening with the slope of that line? And what's happening is that I continue to get a better and better and better and better approximation for the average rate of change, to the point where when I can evaluate the limit, I actually find out what the instantaneous rate of change is at the point x f of x. Now, this is actually a really, really important concept, because now I'm no longer finding the slope of the secant line that connects 2 points. I'm actually finding the slope of the tangent line at exactly f of x. It's only hitting the graph in that 1 point. This is something that I want you to keep in mind. When you see instantaneous rate of change, what I want you to think in your head is slope of the secant, or excuse me, slope of the tangent line. And even more importantly than that, what I want you to keep in mind is this new concept that this unit is all about. When you see instantaneous rate of change, what we mean is slope of the tangent line, and what we mean is the derivative. That's our new big word for this part of the course. We're going to be working with derivatives throughout the remainder of this unit and even into the rest of the course. This is kind of the cornerstone of what we're going to be doing in this calculus class, is working with derivative. So these 3 things, I want you to put them all together, tie them in. If you see derivative, think slope of the tangent line and instantaneous rate of change. If you see instantaneous rate of change, think derivative. Okay? Those things mean exactly the same thing. Now, we're going to actually do some calculations with this, and what I want you to see is that there really isn't a whole lot of calculus here. If you remember when we were working with limits, we talked about the fact that really all there was a whole bunch of algebra, and it ended up breaking down into a whole bunch of algebra with a limit at the end, which really was plug in this value for whatever your independent variable is. Same thing here. There's a lot of algebra. You're going to have to really have a good grasp of what's going on algebraically, and then we're going to apply just a little bit of calculus to that. Okay? This right here, this statement right here, something that you definitely need to know. This is the definition of a limit, the limit definition. And we're going to call that f prime. So we're going to call that f prime of x. Okay, so let's take a look at how to actually find what a derivative is, or the derivative of a function, if we know what the function is and we can apply the limit to that function. So let's take a look at an example of this, and I'll do something that's got a little bit of simplicity as far as the algebra goes, and then we'll look at something that maybe is a little bit more complicated, just so you can kind of see that really still just algebra. It's just going to be some more complicated algebra. So let's say that we've got the function f of x equals 2x squared minus x plus 3, and we're asked to find f prime of x. What is f prime of x? Okay, so the way that we're going to do that is we're going to apply our limit definition of derivative. This is going to be a lot of algebra. Like I said, I'm going to find the limit as h tends to 0 of f of x plus h minus f of x divided by x plus h minus x. I'm going to simplify this a little bit, and I'm even going to make this easier for us to remember. X plus h minus x, the x's cancel, and so really this is just the limit as h tends to 0 of f of x plus h minus f of x, all divided by h. Now, really, it doesn't matter what that function is. Not going to be able to plug in 0 for h here, because no matter what, I'm going to have a division by 0 problem. So we're going to have to see if we can do some simplification here. So, first thing I'm going to do is I'm going to evaluate this numerator as best as I can. So, to find f of x plus h, I'm going to put x plus h in place of all of the x's here. Okay, this is one of the things that seems to be a problem for students sometimes. Sometimes they just want to add an h to the end of that. Don't do that. We want to put x plus h in place of all of the x's here. So that's going to give me 2 times the quantity x plus h squared, replacing x with x plus h, minus x plus h, replacing that x with x plus h, plus 3. And then I'm going to subtract, so all of that is my f of x plus h. I'm going to subtract f of x. Again, be careful. Make sure that you're actually subtracting the entirety of f of x. So we're going to subtract 2x squared minus x plus 3. All of that is going to be divided by h. Okay? Now, here's where the algebra comes into play. Here's something I forgot. Don't do this. You need to have in every one of these steps, like we said when we were talking about limits, we haven't applied the limit yet, so we should make sure that we include it all the way along the way. Okay, so next step, I'm just going to start expanding that numerator, see what happens. So I'm going to take the limit as h goes to 0 of 2 times, let's see, x plus h squared, that's going to be x squared plus 2xh plus h squared. Remember, when you're multiplying two binomials together, don't forget your middle term here. Minus, I'm going to go ahead and distribute that negative through that parenthesis, so I'll have x minus h plus 3. I'm going to distribute this negative through that parenthesis there, and that's going to give me minus 2x squared plus x minus 3, and all of that is divided by h. Looks like it's getting pretty nasty here. Let's see if we can simplify things a little bit more. Next thing I can do, I can distribute that 2 through that set of parentheses there. That's going to get me 2x squared plus 4xh plus 2h squared minus x minus 3. I'm sorry, minus x minus h. Went too fast there. Plus 3, and then minus 2x squared plus x minus 3. And once again, don't forget you need your limit as h goes to 0, and all of that is divided by h. So I've got this thing expanded, and when you get it expanded, now let's see if we can collect like terms. Well, I've got a 2x squared here, and I have a minus 2x squared here. So this term and this term are going to cancel each other out. I have a minus x here and a plus x here, so this term and this term are going to cancel each other out. And then I have a plus 3 here and a minus 3 here, so that term and that term are going to cancel each other out. So let's see what we have left here. We've got the limit as h goes to 0. Let's see, I have a 4xh plus 2h squared minus h, and then it looks like everything else got canceled out. So this is all I have left, all divided by h. And now I notice that in the numerator here, everything has an h. And so I'm going to factor that h out of the numerator. So I get the limit as h goes to 0 of h times the quantity 4x plus 2h minus 1, all divided by h. And now, because I don't care what happens at h, I only care what's happening around h, I'm allowed to cancel those h's out. That was handy. That was exactly what I needed to be able to do because I want to be able to plug in 0 for h to do my calculus. So now I have the limit as h goes to 0 of 4x plus 2h minus 1. And now I can plug in 0 for h, and I get 4x minus 1. Algebra, 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 algebra. Little bitty calculus here at the end. There's my f prime, my derivative function. So I know exactly what the function or the instantaneous rate of change is at any point on the curve. Now, let's say that we wanted to find, for this particular problem, for this function, let's say that they asked us to find, say, f prime of 2. Well, now that I have this derivative function, that's easy to do. Now they're asking me to find the instantaneous rate of change at exactly x equals 2. Well, now that I have what the instantaneous rate of change is over the entire function, all I have to do is evaluate f prime of 2. That's going to be 4 times 2 minus 1. So the instantaneous rate of change at x equals 2 is going to be 7. Okay? So that's how we find the instantaneous rate of change. Now, there is another way to do this. I don't think it's going to be any easier as far as the algebra goes. It's still kind of the same process. But if you know you're going to have to evaluate f prime of 2, rather than going through with all of these x's here, you can replace all of the x's with a 2 there, and go from there. Should get you right back where we have right here. Shouldn't matter at all. Okay, so we can do f of 2 plus h minus f of 2 over h, and then this would be 2 plus h, that would be 2 plus h. We could actually evaluate that numerically now, and then what we should be able to do is kind of simplify this whole thing. Everything should cancel out the same way. The algebra should work out the same, but rather than having a function value at the end, we would get directly to 7 here. So I always found it easier to just find the derivative function, That way, regardless of what point they asked me for, I could actually find out what that was once I have the derivative function. Okay, so that's kind of the process here. Like I said, a lot of algebra. You'll have to be really good with your algebra skills here. Let's take a look at another one that maybe is a little bit more difficult here. Not going to look as difficult when we first put it up, but probably going to tax the algebra skills a little bit more. Let's say that we had the function f of x is equal to 1 over x, and I want to find f prime of 3. Okay, there's my question. We want to find the instantaneous rate of change at x equals 3, the value of the derivative at x equals 3. Notice how I keep continuing to put that terminology together. Okay, same thing that we did before. We're going to start off with the limit as h goes to 0 of f of x plus h minus f of x divided by h. And we're going to plug in the function as we know it here. So that's going to be the limit as h tends to 0 of 1 over x plus h, again, plugging x plus h in for my x value, minus 1 over x, all divided by h. So I have a compound fraction here that kind of looks like this is going to be a little bit more difficult to do. It's actually not so bad though. What I'm going to do here, I'm going to multiply top and bottom by whatever that common denominator was. So if I do that, again, just multiplying by 1, so I'm allowed to do it. I'm not changing the problem at all because I'm multiplying by 1. And what happens when I do that is, when I multiply the first term in the numerator by this, the x plus h will cancel. So I'm going to get the limit as h tends to 0 of x minus, and then when I multiply this numerator times this fraction here, the x's will cancel and I'll get left with x plus h, all divided by, now in the numerator, not much I can do, or excuse me, in the denominator, there's not much I can do here. So I'm just going to leave that separated. I'm going to make it h times x plus h. So it looks like I kind of made this worse because I put more h's in the denominator than what I started with. It's actually going to work out pretty well here though. So let's see if we can do some simplification here. I'm not going to rewrite this, I'm just going to distribute that negative through there. And when I do that, that's going to give me x minus h. And now, when I cancel out those x's, I get the limit as h goes to 0, x minus x goes away. So I have negative h over h times x plus h. And now, I have an h term in the numerator, I have an h term in the denominator. Those will cancel each other out, but be careful here. That doesn't make the numerator 0, it makes it negative 1 here. So I'm going to have the limit as h goes to 0 of negative 1 over x times x plus h. Now, keep in mind that I still have an h in the denominator here, but it's actually not causing me a problem anymore. Now I can plug in 0 for h, and I'm going to get negative 1 over x times x plus 0, which is just going to be negative 1 over x squared. And there's my derivative function. There's f prime of x. So the question asked me to find f prime of 3. So now all I have to do is say, okay, f prime of 3 is going to be negative 1 over 3 squared, which is negative 1/9. There's my instantaneous rate of change, or the value of the derivative, or the slope of the tangent line at x equals 3 for this function 1 over x. Now, a lot of algebra, really complicated here, probably a better way to do this. That's what the next few videos are going to be about.